And welcome to the Digital Systems Lab podcast, where we break down complex concepts in electronics and computing into simple, digestible ideas. I'm the professor, and today we're diving into the world of FPGAs, Field Programmable Gate Arrays. Today's episode is all about Field Programmable Gate Arrays, or FPGAs. You've probably heard the term in passing, but what are they really, and why are they so powerful in digital design? Let's find out. Think of an FPGA as a blank canvas. Unlike traditional integrated circuits that are set in stone at the factory, an FPGA can be reprogrammed to do whatever digital task you need. You get configurable logic blocks, programmable connections, input-output blocks, memory, and even digital signal processors, all in one chip. It's like the digital Lego bricks for engineers. Now, how do we paint on that canvas? Well, there are two main ways. One is using schematic-based tools. Think drag and drop wiring, but that's not very efficient. The real power comes from writing code using something called a hardware description language, or HDL. The two big ones are VHDL and Verilog. Let's consider a design example, a modulo 11 counter. In the old school, discrete logic world, you'd need multiple chips, AND gates, inverters, counters, all wired together. That's messy, error-prone, and hard to update. If you wanted to change the design, you'd need to rewire everything and maybe even use different chips. This is like trying to change the story of a movie after it's been filmed. Now imagine doing the same design using software. You sketch it, simulate it to make sure it works, and then load it onto your FPGA. No wires, no soldering, just click, compile, and go. Here's a taste of what that looks like in code, VHDL to be exact. This snippet describes a Mod 11 counter that resets when it hits 11. If you've ever coded in a high-level language, you'll see some similarities. But this code directly describes hardware behavior, not just logic, but timing too. Let's talk architecture. The heart of an FPGA is the configurable logic block, or CLB. These handle both combinational logic, where outputs depend only on current inputs, and sequential logic, where past input history matters. An array of configurable logic blocks which are programmed by the designer to implement a specific application. The CLBs are interconnected through both vertical and horizontal channels. The behavior of the FPGA is programmed via hardware description languages such as VHDL or Verilog, or via schematics. The advantages are that this is fast, allows real-time applications, allows parallel data processing. The disadvantages are that this is costly, not easy to program, slower than an ASIC that have designed for a specific task, and they draw more power. Each logic block contains something called a lookup table, or a LUT, L-U-T. This is like a tiny memory that stores output values for every combination of inputs. No need for physical gates. Super efficient and lightning fast. Here's how it works. The input bits select a specific memory location, and the LUT, the LUT, spits out the corresponding logic value, elegant and effective. Add some associated logic like multiplexers, and now you can combine LUT outputs and decide dynamically which one to use. It's modular, flexible, and powerful. Some functions are built directly into the chip as hardcore blocks, like microprocessors. These can't be changed. Others, called softcore, are customizable. You get the best of both worlds. Let's take a closer look at something called hardcore logic inside FPGAs. Picture this. An FPGA is like a giant neighborhood full of tiny programmable buildings. Each one is called a CLB, a configurable logic block. Most of them are blank, waiting for you to tell them what to do. But in the middle, there's a section that's already set in stone. This is the hardcore region. It's like a pre-built part of town. These blocks are programmed by the manufacturer to handle specific tasks. You don't get to change them, but that's not a bad thing. Why? Because they're optimized, they're fast, and they're reliable. A common example, microprocessors. You get a full CPU built right into your FPGA fabric, ready to go. No need to design it yourself. Now, the rest of the chip. The majority of it is what we call softcore. This part is totally under your control. You write the code, you define the function, you own the logic. So hardcore means fixed and fast. Softcore means flexible and custom. And together, they give you the best of both worlds. Manufacturers sometimes call these blocks different names like LABs, logic array blocks. Regardless of the label, they house all sorts of goodies. ADCs, DACs, flash memory, and DSPs. Let's zoom in one of the coolest things about FPGAs, embedded functions. If you're picturing a chaotic jungle of wires, think again. This is more like a highly organized city grid. What you're looking at here is the internal map of an FPGA. The blocks you see are logic array blocks, or LABs. Some companies call them CLBs, or configurable logic blocks. It's just a different label for the same idea. Now, in between these LABs are some special purpose areas. These are embedded memory blocks, DSP blocks, and input-output elements. Think of them as specialized departments inside a high-tech building. Embedded memory blocks store data your design needs to access quickly. DSP blocks stands for Digital Signal Processing. They handle heavy-duty number crunching like audio filtering or image manipulation. And those I/O, input-output elements, they're the interface that talk to the outside world. Buttons, switches, sensors, you name it. Over on the right side, there's a massive embedded memory block. That's like a centralized library, ready to deliver huge chunks of data without breaking a sweat. Bottom line, this isn't just a chip. It's a smart, modular city where each block knows exactly what job it has and how to communicate with its neighbors. And you, the designer, are the city planner. Want to convert sound waves into digital data? That's your ADC, your analog to digital converter. Need to turn bits back into analog voltage? That's your DAC, your digital to analog converter. DSP blocks help with mass heavy tasks, like filtering audio signals, just with code instead of physical filters. Designing with an FPGA follows a workflow. Write the code, simulate it, compile it, and upload it. Tools like Quartus make this smooth and fast. Let's walk through how a digital design becomes a working FPGA circuit. It's a journey, almost like building a house from blueprints to the final structure. We start with design entry. This is where you create your design either by drawing a schematic or by writing HDL code, hardware description language, like VHDL or Verilog. It's your plan, your blueprint. Once the design is in place, we move to functional simulation. This is the does it work step. We simulate the logic to check if it behaves correctly before we ever touch the hardware. If it fails, we go back and fix the design. When it passes simulation, we go to synthesis. Here, your abstract design gets turned into actual digital logic that the FPGA understands, like translating your house plan into materials and measurements. Then comes implementation. The synthesized logic is placed and routed inside the FPGA layout. Now it knows where everything lives, what connects to what. Next, we verify it all with a timing simulation. This step checks whether your circuit will run fast enough and still function correctly in real time, just like making sure the plumbing and electricity won't overload the system. If that passes, then the final step is device programming. We load the design onto the FPGA chip itself. Your logic is now alive in silicon, ready to run, react, and compute. And just like that, your digital idea becomes real hardware. We use the DE10-Lite board in our lab. It's a compact, powerful FPGA development kit. You've got a 7-segment display, buttons, switches, LEDs, perfect for hands-on learning. Now that we've explored the design process, let's get to know the hardware you'll be working with. The Max 10 FPGA board, specifically the 10M50DA F484 model. It's like a digital playground packed with features for hands-on learning and real-world projects. At the heart of the board is the FPGA chip. This is your reconfigurable brain, but what makes this board so powerful are all the tools that surround it. Let's start on the left side. You've got a USB blaster for programming and communication. The FT245 chip and Max2 handle data transfer between your computer and the FPGA. Think of them as interpreters. Just below that, you'll find an Arduino header. Yes, this board is Arduino compatible, which means you can plug in sensors, modules, or shields just like you would with an Arduino Uno. Next to that is an analog buffer and ADC, analog to digital converter. This lets your FPGA understand real-world signals, like temperature or light, that aren't naturally digital. Right below the FPGA, you've got a 7-segment display, great for visual output like numbers or letters, 10 LEDs for status indicators, 10 slide switches, and 2 push buttons, all debounced to prevent noisy signals. Now on the right side, there's an onboard clock, vital for synchronized logic. 64 megabytes of SD RAM, giving you plenty of memory to work with. An accelerometer for motion sensing, perfect for robotics or gesture-controlled projects. Resistors and a VGA output, so yes, you can drive a monitor with this board. And finally, a GPIO header that opens the door to countless external devices. It's not just a board, it's an entire development ecosystem. Whether you're building a digital counter, a video controller, or a motion sensor interface, this FPGA board has the tools to make it happen. Now let's get hands-on and talk about some visual LEDs. The Max 10 FPGA board gives us 10 red LEDs labeled LDR0 through LDR9 that we can control directly through code. Each LED is connected to a specific pin on the FPGA. For example, LED0 is wired to pin A8. LED1 is on pin A9. And it continues in sequence all the way up to LED9, which is on pin B11. These pins follow a 30.3 low voltage TTL logic standard. That's low voltage TTL logic. So when you write a logic 1 or 0 to these pins, the LED either turns off or on depending on the design. And here's the key. All the LEDs are active high, which means you output a logic 1, the LED turns on. Set it to 0 and it turns off. You'll see resistors in series. These prevent too much current from flowing through and burning out your LEDs. So they're not just there for decoration. They're a crucial part of the circuit's health. This setup makes LEDs the perfect tool for debugging. Want to confirm your logic is working? Light up an LED. Need to display binary values? Use multiple LEDs together like a mini light show. Simple, powerful, and perfect for learning how digital logic interacts with the physical world. Each segment of the display lights up with a logic low signal, meaning a 0 turns the light on. The segments labeled A through G create the numbers you see. The push buttons are momentary, meaning they only stay pressed as long as you hold them. Pressing one sends a logic low into the system, just like flipping a digital switch. Slide switches behave a bit differently. They have a default weak signal which can cause LEDs to glow faintly, but with proper configuration you can eliminate that and get clean logic behavior. The board comes with system clocks, signals that help synchronize your design, kind of like a metronome for your circuit. And last but not least, general purpose input-output pins, GPIOs. These let you connect to keypads, sensors, LCD screens, you name it. If it speaks digital, the FPGA can talk to it. And I want to thank you for tuning in to Digital Systems Lab podcast, where we broke down complex concepts in electronics and computing into simple, digestible ideas. I'm the professor, and today we dove into the world of FPGAs, Field Programmable Gate Arrays. Today's episode was all about Field Programmable Gate Arrays, or FPGAs. You've now heard the term in and know what they are for, and why are they so powerful in digital design. Thank you, and we'll see you again on the next episode.